This is everyday stoichiometry and mole A to mole B stoichiometry. What is stoichiometry? Stoichiometry is the calculation of the quantities of reactants and products involved in a chemical reaction. So let's look at everyday stoichiometry. We do this every day. So let's look at this is the question. Because for you to do stoichiometry, you have to have a balanced equation. And in everyday stoichiometry, we prepare sandwich every day. Look at this. We have 2 slices of bread plus 1 slice of cheese. We end up with 1 sandwich. Okay? So this is grilled sandwich. So given the recipe for 1 person, we write the equation. It says write the equation if you are preparing grilled sandwich for a family of 4. So think about it. You made this delicious grilled sandwich, and some people are going to visit you. You say, oh, I'm going to make that sandwich. Now, you have to make it for 4. How will you do it? Write the equation. And then you ask yourself, how many sandwich can you make with 3 slices of cheese? How many slices of cheese do you need to make 2 sandwich? How many slices of bread do you need if you have 5 slices of cheese? We do this every day. Here we go. So here's the answer. You're making sandwich for 4. Look at it. We are making use of these numbers called coefficients. Okay? We are using the coefficients to do that calculation of figuring out how many of these we need for a family of 4. So you see, how many sandwich can you make with 3 slices of cheese? Okay, slices of cheese, 3 slices of cheese. So you see, sandwich and cheese, they're 1-to-1 ratio. Okay, so we make 3 sandwich. Then how many slices of cheese do you need to make 3 sandwich? Okay, that will be 3 slices of cheese. Then how many slices of bread do you need if you have 5 slices of cheese? Okay, it will be 10 slices of bread. So in each of these, we are calculating the quantity of either sandwich, which is the product, or we are calculating about the quantity of reactant that can be used. Okay, like how many slices of bread can you use with slices of cheese? So it's about the reactants and the products. We are calculating the quantities of reactants and products. So let's look at the ratio, which is here. We use coefficient as ratio. We say, what is the ratio of B, that is slices of bread, to slices of cheese? What is the ratio of slices of cheese to slices of bread? What is the ratio of sandwich to slices of cheese? What is the ratio of slices of cheese to sandwich? So in doing this, we have to use these coefficients as ratios. So if we're able to look at that, we have the slice of bread to cheese is 2-to-1. Ratio of C to B is 1 to, this should be 1-to-2. 1-to-2. Cheese to bread should be 1-to-2. You have to correct it here. The ratio of sandwich to C will be 1-to-1. The ratio of slices of cheese to sandwich is 1-to-1. So this is slices of cheese to bread is 1-to-2. So I made that correction. Now, if you want to, we can answer this without really doing any calculation, but let's do the calculation so that it will be easy for us to do it in chemistry, because everything, the way it's done in everyday life, everyday stoichiometry, that's exactly what we do in chemistry. The only difference is here we are using bread and cheese and sandwich. You say, how many slices of bread do you need if you have 5 slices of cheese? Let's look at this problem. Or you can try it and see how you do it. I don't mean just answering it orally. I mean doing it the way you would write, using dimensional analysis to do it. Let's try that. Okay, let's do it. It says we have a balanced equation. This is for one person, the recipe for one person. So how many slices of bread do you need if you have 5 slices of cheese? We know this, we need, you see, how many slices of bread? Okay. So what's the relationship between slices of cheese, slices of bread in this balanced equation? We will see that we use ratio. So from the balanced equation, we can say 2 slices of bread over 1 slice of cheese, or 1 slice of cheese over 2 slices of bread. This is the ratios. Okay, I put it in fraction form because we will use it in calculation. Now, we are going from, like we are doing dimensional analysis, we follow the same steps. We are going from slice of cheese, to slice of bread, using ratio from the balanced equation. Now, we want to figure out how many slices of bread. So we start with what we know. We know 5 slices of cheese. Slices of cheese over 1. Then we repeat slices of cheese because we want to get rid of that. Oh, then slices of bread. Slices of cheese to slices of bread. So there's 2 slices of bread and 1 slice of cheese here. We cross this out. So this is now like conversion factor. So we need 10 slices of bread. You did this for 1 second. For 1 second, you already figured it out. But this is actually what happens. And this is what we do every day. That's what we do in everyday life. We want to bake something. We are doing these calculations. Okay. Let's look at these 2 equations, chemical equations. The first one is everyday stoichiometry, the one we use in everyday stoichiometry, and this is a chemical equation. Okay, just as we use ratio here, we will use these coefficients as ratios too, but this time we call this mole ratio. Remember, mole is used in chemistry in counting. Okay, so what is mole ratio? It is the ratio of moles of one substance to the moles of another substance in a balanced equation. So looking at this particular equation, For every 2 moles of magnesium that react, 2 moles of magnesium oxide is produced. For every 2 moles of magnesium that react, 1 mole of oxygen is required. Look at it here. This, when it's not written, is 1. Okay? For every 1 mole of oxygen that reacts, 2 moles of magnesium is required. 2 moles of magnesium. So for every 1 mole of oxygen that reacts, 2 moles of magnesium oxide. What am I doing here? I keep on messing up. So for every 2 moles of magnesium that react, 1 mole of oxygen is required. For every 1 mole of oxygen that reacts, 2 moles of magnesium is required. This is a proportional relationship, and mole ratios function as conversion factors in stoichiometry problems. They function as conversion factors in stoichiometry. So just like dimensional analysis, this is stoichiometry steps. You first of all have to have write a balanced equation, identify what is given and what you are asked to solve for. Then start a setup with the number and unit that is given on the upper left-hand corner. If converting between moles and mass, use molar mass. If converting between moles and liters, use molarity. If converting between moles and liters of gas at STP, use molar volume. Use mole ratio to convert from the moles of the substance given to the mole of substance needed. This is the core step in all stoichiometry problems. The mole ratio is always determined from the coefficients in a balanced equation. Do the math by multiplying all the values in the numerator and dividing by the product of all values in the denominator. Then check your answer. Okay? Let's look at example 1. Mercury 2 oxide decomposes into mercury and oxygen gas according to the following balanced equation. Now, how many moles of mercury are produced if 24.5 moles of mercury 2 oxide decompose? Remember the meaning of stoichiometry. We are calculating the quantities of either the reactant or the product. Here, we will look at the product, the quantity of the product. So let's look at this example. Let's look at example 1. So how many moles of mercury are produced? Mercury is a product if 24.5 moles of mercury 2 oxide decomposes. Okay, we know this. We do not know this. Okay, so now we are going from one substance to a different substance. Think about the sandwich. We went from either slice of bread to slice of bread, cheese, or from slice of cheese to sandwich. In each of them, we use ratio. So here we use mole ratio because you are going from mole of one substance to mole of a different substance. And this is what stoichiometry is, going from mole of one substance to mole of a different substance. So you ask yourself, are we going from one substance to another substance? If you are doing that, we are using mole ratio. So we are looking at mercury and mercury. So the mole ratio will be 2 moles of mercury 2 oxide over 2 moles of mercury, or 2 moles of mercury over 2 moles of mercury 2 oxide. Now the strategy is we are going from moles of mercury 2 oxide to moles of mercury. This is the easiest question you can ask in stoichiometry. So we want to find moles of mercury. We know we have 24.5 moles of mercury 2 oxide over 1. Then the same, we write mole of mercury 2 oxide, now moles of mercury, which is 2. This is 2. This will cross out. This will divide itself, so this will be 24.5 moles of mercury. You see, it looks like proportion problem 1:1. So that's the first example. Example 2, hydrogen gas and oxygen gas can be generated through electrolysis of water. The balanced chemical equation is this. How many moles of oxygen could be produced from the decomposition of 15 moles of water? Now we want to calculate the amount of oxygen, and we are given the moles of water. We are calculating the quantity of the product. We are calculating the quantity of the product. Let's look at this, look at the example we just talked about. So we know 15 moles of water. We do not know how many moles of oxygen gas. Now, again, we're going from moles of one substance to moles of a different substance. As long as it's moles of one substance to mole of a different substance, we use mole ratio from the balanced equation. And what's mole ratio? We're using the coefficients. So we are talking about water and oxygen. So 2 moles of water over 1 mole of oxygen, or 1 mole of oxygen over 2 moles of water. So the strategy is we are going from moles of water to moles of oxygen, okay, using mole ratio. So we solve, we want to find moles of oxygen. So 15 moles of water over 1 moles of water moles of oxygen. So this is like conversion factor, which is 1 mole to here. So we cross this out, and the answer will be 7.5 moles of oxygen. That's it. Easy. This is the easiest question you can get in stoichiometry. Pause the video and try this practice question. How many moles of potassium chlorate must decompose in order to produce 9 moles of oxygen gas? Okay? Pause the video and try this. Remember the dimensional and the stoichiometry steps. Go back and look at those steps and follow it. So hopefully you pause the video, you did it. So we have 9 moles of oxygen gas. We want to find moles of potassium chlorate. So again, one substance, a different substance. We use mole ratio. Oh, using this balanced equation, mole ratio from this balanced equation, potassium chlorate 2 KCl plus this. That's the balanced equation. So the mole ratio, potassium chlorate, oxygen. So 2 moles of KClO3 over 3 moles of oxygen, or 3 moles of oxygen over 2 moles of potassium chlorate. Then the strategy, we are going from moles of oxygen to moles of potassium chlorate, mole ratio. So we want to solve for moles of potassium chlorate. So we know 9 moles, the same thing, remember? You can always look at that stoichiometry steps. As many times as you think you need it, use it. If you're struggling, then moles of potassium chlorate. So we have 2:3 ratio. So that will be 18/3. 18 divided by 3 will be 6 moles of KClO3. Hopefully, you did well. Let's load, pause the video and do these practice questions. It says sodium chloride is produced from the reaction between sodium metal and chlorine gas. The balanced equation is this. How many moles of sodium chloride could be produced from 9 moles of chlorine gas with excess sodium? How many moles of sodium chloride could be produced from 4.13 moles of sodium in excess chlorine? How many moles of sodium is needed to produce 5.50 moles of sodium chloride? Pause the video and try this. If you don't get this right, it means you have to go back and look at stoichiometry again and all the examples. Let's look at these practice questions together. Okay, we know 9 moles of chlorine gas. We do not know how many moles of sodium chloride. Again, we are going from one substance to a different substance. So from the balanced equation, remember when this is not written, it means 1. We have 1 mole of chlorine gas over 2 moles of sodium chloride, or 2 moles of sodium chloride over 1 mole of chlorine gas. So the strategy here is we are going from moles of chlorine gas to moles of sodium chloride using mole ratio. So we are solving for moles of sodium chloride. This is then, look at the stoichiometry steps again. If you are still struggling, moles of chlorine gas, now moles of sodium chloride. So this one is the correct. This is now conversion factor. We cross this out, and that will be equal to 80 moles of sodium chloride. 80 moles of sodium chloride. Then you want to put it in scientific notation, 1.8 times 10 to 1 moles of sodium chloride. Now, we are using the same, for the second one, we are using the same balanced equation. So again, we underline, we circle, mole ratio again, the same balanced equation. Now we are looking at sodium chloride and moles of sodium. So the mole ratio will be 2 moles of sodium over 2 moles of sodium chloride, or 2 moles of sodium chloride over 1 mole of sodium. Okay. Again, the strategy, we are going from moles of sodium to moles of sodium chloride using mole ratio. So we have solving for moles of sodium chloride. That will be 4.13 moles of sodium over 1 times, again, moles of sodium, moles of NaCl. The ratio is 2. Wait a minute, sodium is what? I'm sorry. Sodium is 2 here. How did I mess up here? 2 to 2. So this is 2, this is 2. This cross out. This cross out. So you give moles of sodium chloride. Hopefully, you got this right. It's very, very easy. You can't get anything easier than this. Then, so now, the last question, I give you the answer. This is the answer to the last question. Hopefully, you did it right. Thank you. I hope you understood everything.